be talking about so today I will be talking about secure non-interactive simulation. This is a joint work with my students Hamid and Hai. The objective of this talk is to lay the foundations of secure non-interactive simulation, motivate this research through its applications in secure multi-party computation, and discuss the potential for exciting new research directions. Let me introduce a secure multi-party computation first. I'm choosing to introduce this in the pre-processing model because most practical MPC protocols are designed in this framework, and two, this framework naturally leads to several exciting research problems in information theory, which will be of interest in this talk. I will illustrate these aspects using representative research conducted by my group in secure multi-party computation. So the pre-processing model has two phases, the offline phase and the online phase. During the offline phase, parties get together, interact, and generate correlated samples. They could be random Beaver triples, random samples from correlated noise, or correlated private randomness. However, this step is extremely computationally expensive. And this step, in fact, is independent of the target secure computation and the private inputs that parties will use. In this figure, I'm only using two-party case as a representative example. These definitions extend to the multi-party case. In the online case, in the online phase, parties use the previously generated correlated private randomness in a fast protocol. This protocol is in fact information theoretically secure if the pre-processing phase produces a secure output. Notice that this model separates the task of secure computation into two phases, the offline phase and the online phase. Each phase had its own objectives and challenges to address. And this is an extremely modular way of analyzing the efficiency and power of secure multi-party computation. This model is is particularly popular because there are several practical success stories for MPC which build on this model. Now let me illustrate how one can establish several research directions starting from this particular model. Observe that the pre-processing phase creates samples ahead of time. So it is natural to wonder, what if an adversary performs side channel attacks to compromise some of these samples? Then one has to investigate privacy amplification or information reconciliation problems in the cryptographic context. In particular, one can wonder what is the most robust pre-processing phase. In other words, can we measure the robustness of a pre-processing phase to adversarial attacks? In one of our previous works, which I presented last year at this venue, we discussed one such measure, which is an extension of common information to the cryptographic context. A natural problem for secure multi-party computation is to ask whether secure computation is feasible under certain constraints, what is the most efficient protocol that's possible, and consequently, rate and capacity of secure computations are natural directions of research. The topic that we'll cover in today's talk is in this general scope of research. Further, one can also ask, what is the round or communication complexity of secure computation protocols? This is this is an investigation of the information complexity of secure computation. We have an upcoming work which resolves a long-standing open problem in this field. This problem was open since the 1980s, and this determines the round and communication complexity of secure computation protocols. And most importantly, this model is extremely powerful in generating security solutions. For example, we introduced this notion of an inverse multiplication embedding problem, where one is provided with a multiplication oracle over the extended field. And the question is, how many multiplications over the base field can we perform by using one call to this multiplication oracle over the extension field? This particular problem has had significant practical impact through its applications in secure multi-party computation and homomorphic encryption. Further, some of our research in this model has also led to privacy-preserving solutions in privacy-preserving training and inference problems in machine learning. With that background, let me motivate the primary problem which leads to the study of secure non-interactive simulation. We have seen that fast online protocols typically need very well-structured correlated randomness to be generated during the pre-processing phase. However, these well-structured correlations are extremely computationally expensive to generate. On the other hand, there are easy to generate correlated private randomness, like samples from noisy sources. We can use these in the online phase. However, we have seen that the typical online phase is significantly slower. An ideal resolution of this problem will be to use these cheap sources and non-interactively and efficiently convert them into well-structured correlated private randomness. So this possibility leads us to study the problem of secure non-interactive simulation. Let me introduce the model formally. So our target distribution is UV, and our source distribution is XY, and we have N independent samples from the source distribution. So two parties generate N independent samples from the source distribution. Alice receives XN, Bob receives YN. Additionally, Alice has access to independent private randomness. Similarly, Bob also has access to independent private randomness. Alice uses her samples to generate the output U prime by applying a function f, and Bob generates his output by applying a function g to his samples. Sorry, there is a typo, this should be yn. The correctness of secure non-interactive simulation insists that the joint distribution of the output of the parties is close to the actual target distribution. The security of honest Bob against corrupt Alice states that Alice's sample xn conditioned on a particular u prime and v prime should be independent of her output u. This might seem ad hoc. However, there is a reason for defining security in this manner. This is consistent with universally composable definition of security that is commonplace in secure computation. Likewise, the security of honest Bob against corrupt, honest Alice against corrupt Bob insists that the sample distribution yn conditioned on u prime and v prime should be independent of u. That is, this distribution is simulatable only using Bob's output V. These three conditions define the in this model define secure non-interactive simulation. If one is interested in studying the rate of secure non-interactive simulation, then we consider the target distribution to be M independent samples of joint distribution UV. And our objective is to characterize the maximum achievable ratio M is to N. This is the natural notion of a single letter characterization of rate. This model, in fact, looks similar to several models that are considered in information theory and theoretical computer science. Let me mention a few representative ones in here. So recently, Boyle et al. Considered exactly the same problem. However, in their context, the parties Alice and Bob have bounded computational power. This notion has been extremely useful to construct efficient, practical MPC solution. And our notion of secure non-interactive simulation is an information theoretic analog of pseudo-correlation generators. That is, the parties have unbounded computational power. A classical problem in information theory considers an identical model that I presented earlier. However, there is no restriction of security. So, secure non-interactive simulation is a cryptographic extension of non-interactive simulation of joint distributions, which has been well studied in information theory for quite some time now. Another problem that is quite common and is well studied in theoretical computer science is the problem of non-interactive correlation distillation. Here, parties interact to, non-interactively create copies of shared keys. That is, it is a restriction of secure non-interactive simulation where the target distribution is restricted to be shared keys. In cryptography, if your target is to perform general secure multi-party computation, shared keys are not sufficient for that purpose. You need to create more complicated correlated private randomness, and therefore it's a generalization of this notion. In 2015, Garg, Ishai, Kushlavit, Ostrowski, and Sahai introduced a notion of one-way secure computation, a notion of secure multi-party computation where only one party speaks and everyone else listens. So secure non-interactive simulation is a restriction of one-way secure computation where no interaction is permitted. At this point, given these connections to several related problems, it is easy to see that we have independent motivation. We have independent motivation to study secure non-interactive simulation. For example, one can consider the problem of controlling agents under limited or no interaction, where these agents could fall under adversarial control. Another problem is to construct a robust framework for secure multi-party computation, something analogous to what Maurer proposed. However, this is in the context of secure multi-party computation and not just a privacy amplification and not just generating keys. A more theoretically a theoretical motivation arises from studying cryptographic complexity. In this study, the motivation is to understand the cost of constructing cryptographic primitives. For example, the computation cost, communication cost, the round complexity of constructing one kind of primitive from other kind of cryptographic primitives. So now that we have several independent motivations. Let me introduce the main protagonists of today's talk. So in today's talk, we will be considering correlated private randomness generated by two channels. For example, the first one that we consider is noise generated by binary symmetric source. In this, a party obtains a random bit. I want to emphasize that in this talk, I will be using a multiplicative notion. So 0 represents +1, -1 to the power 0, and 1 represents, -1 represents the bit 1, that is -1 to the power 1. And the second party receives a correlated bit, which is identical to the bit that the first party receives with probability 1 minus epsilon, and it is flipped with probability epsilon. I'm representing this using a parameter rho, which is 1 minus 2 epsilon, where epsilon is the probability of flipping the bits. The reason I'm using rho is that this corresponds to something called the maximal correlation of a joint distribution, which is a prominent quantity studied in information theory, and it will be crucial in our results as well. The second correlated noise that we will study is the noise generated from a binary erasure source. So again, Alice receives a random bit +1 or -1. With probability 1 minus epsilon, Bob receives the bit that Alice received. Otherwise, the bit is erased. And again, I'm using multiplicative notation to represent bits, this information. In this case, the maximal correlation of a binary erasure source is actually square root of 1 minus epsilon, where epsilon is the erasure probability. And again, I will keep highlighting this, that rho represents the maximal correlation of this source. So let's begin with an insecure reduction and trying to understand why this reduction is insecure. So to begin, we are given correlated samples from a binary erasure source. Alice has a random bit. Bob receives the bit with probability 1 minus epsilon. Otherwise, the bit is erased. And then reduction that Alice and Bob perform is the following. Alice outputs the same bit as X. Bob outputs the bit Y if Y is +1 or -1. Otherwise, it outputs a random sample +1 or -1. First, observe that U prime is equal to V prime with probability 1 minus epsilon by 2. And with probability epsilon by 2, U prime and V prime are different. That is, we have implemented a binary symmetric source where the symbols are flipped with probability epsilon by 2. However, this construction or reduction is insecure. So let me be more precise. This construction is correct. The joint distribution of the output is correct. It is secure against a corrupt Alice. However, it is insecure against corrupt Bob. One can observe that the conditional distribution of Bob's sample Y is not independent of U prime. If we fix V prime, this distribution depends on U prime as well. Therefore, this construction is insecure. In fact, we will prove that no such construction is possible. Okay. Next, let us consider a secure reduction. In this case, we have a binary symmetric source with that flips the symbols with probability epsilon. And our objective is to construct a new binary symmetric source whose maximal correlation is square of the sources correlation, maximal correlation. So in this case, we consider two independent samples that Alice has, and Bob has correlated samples. And the construction is very simple. Alice outputs the product of the two samples, and Bob outputs the product of the two input samples. We can prove that this construction is in fact secure. Okay. So now we are moving to the technical part of the talk. The results that I cover in this talk will primarily be covering the results from two of our papers. The first paper is accepted to appear at Eurocrypt this year, and the second work is currently under submission. An identical primitive was also independently proposed by Agarwal, Narayan, Pathak, Prabhakaran, and Rehan, and this work also appears at Eurocrypt 2022. There are significant differences between the approaches, however. We follow techniques from harmonic analysis while they followed techniques from matrix analysis, and their techniques does not, their work do not consider rate. They only consider feasibility of secure non-interactive simulation. So let me mention some representative results that I will present in this talk. First, we show that access to private randomness is in fact useless. That is, if there is a randomized secure non-interactive simulation of a target from a source, then there exists a deterministic simulation of the same target using some additional number of source samples. However, this result is not useful if we are interested in studying the rate of secure non-interactive simulation, because it uses more number of source samples. So we have a sample preserving de-randomization result as well, which says that there is a deterministic simulation of the target from the source that preserves the number of source samples. However, the insecurity becomes something like a square root of the insecurity. So essentially, these two results say that access to local, private, independent randomness is useless for secure non-interactive simulation. So our Eurocrypt paper first proves that it is impossible to generate samples from erasure channel starting from samples from symmetric source. In fact, the other direction is also impossible. However, if you are interested in generating samples from a binary symmetric source of maximal correlation rho prime from a binary symmetric source of maximal correlation rho, we will call this self-simulation. Then we prove that rho prime has to be an integral power of rho. In this context, the rate of SNIS is at most 1 by k. And we prove a very strong result that shows that if you have a secure non-interactive simulation that has insecurity tending to 0, then we can error correct the reduction to construct a perfectly secure reduction. Such results are extremely rare in cryptography. In fact, we prove a very strong dichotomy result. We prove that any secure non-interactive simulation will be perfectly secure, or this will be constant insecure. Interestingly, typically when we think of secure multi-party computation, we think that relying on more computational power or more interaction or more samples from correlated private randomness, we can reduce insecurity. What our result shows is that round complexity or the interaction is crucial. Otherwise, Otherwise, having insecurity tend to 0 is impossible. We prove similar results for self-simulation of binary eraser, noisy samples from binary erasure channel as well. However, in this talk, I will be considering primarily results from binary symmetric source because there are very interesting open problems that are left open by our work in that context. In the next work, we consider the secure non-interactive simulation of BSS or BES targets from arbitrary general sources. And we show again that there is a dichotomy that either reductions are perfectly secure or they are inverse polynomially insecure. In fact, we give an algorithm that if you want to find out whether it is feasible for a SNIS to exist, then there are only a constant number of functions that one has to test, and then one can determine whether such a simulation is possible or not. We prove a upper bound on the rate of such simulation. Let's not go into the formula that is written here. I will come back to this result later in the talk. And most fascinatingly, we prove that in non-linear reductions are significantly more powerful than linear reductions. In fact, there are rate achieving non-linear reductions, and for that particular reduction, no linear reduction can be feasible. I will exhibit this result later in this talk. This is extremely fascinating because this shows that non-linear cryptographic construction are inherently stronger than linear constructions, which is not typically known in most contexts. So let's start with some representative, some warm-up results. So first, let us try to prove that the impossibility of generating a target BES from a source BSS. This result is actually known to be infeasible for non-interactive simulation in the context of non-interactive simulation, as well as in the context of one-way secure computation. And remember, secure non-interactive simulation is a stronger form of non-interactive simulation where we additionally insist on security. In fact, it is also a stronger version of one-way secure computation where we also insist that parties do not communicate with each other. So these impossibilities naturally carry over to our context. Let me provide a very high-level overview of how these proofs work. So these proofs essentially show that if there is an output sample of Alice that occurs with a constant probability, and there is a Bob sample that occurs with constant probability, then they occur simultaneously also with constant probability. So reverse hypercontractivity is a technical tool that proves such results, and Harris-Gleichman inequality is also such a technique that helps prove similar results for downward closed sets. Okay, and downward closed sets naturally occur in cryptographic notions because in cryptography, erasure of information is insecure, that is not allowed. So the notion of downward closed sets arises naturally in this context. Now, let us try to prove that it is impossible to prove generate samples from a binary symmetric source starting from a binary erasure source as the source distribution. I want to add that this problem is open both in the set of in the context of non-interactive simulation and one-way secure computation, and this is a very long-standing open problem in this in non-interactive simulation, and is thought to be extremely challenging. However, in our context, we will use the constraint of security to prove this result. So let me highlight the proof overview now. Let's fix a source distribution. Let's fix a target distribution. We'll prove by we'll prove this using proof by contradiction. Suppose there is a secure simulation of the target from the source using multiple independent samples of the source. The first step here, or the 0th step, is to apply the de-randomization result to claim that there are deterministic reduction functions that achieve similar insecurity. So let's abstract that result here. The next step is to algebraize the definition of security. So for the purpose of this talk, just think of these matrices T and T prime, T bar, as stochastic matrices that are defined by the source distribution. So the notion of security translates into 3 constraints that basically says that the function f, the reduction function f, is roughly balanced. The reduction function g is roughly balanced. If you apply the adjoint Markov operator T bar on f, it is similar to g, that it is parallel to g. And if you apply the Markov operator on the reduction function g, then it is parallel to f. So let us abstract these 3 constraints. Next, using the 2 constraints that I'm highlighting, we can get an approximate eigenvector problem. And using triangle inequality, we can conclude that T bar of f is parallel to f. That is, f is an approximate eigenvector of the matrix T bar. Starting from this property, there are some very interesting conclusions that one can draw. The first observation is that the product of the matrices T bar in fact corresponds to the Bonami-Beckner noise operator T subscript rho square. Then one can study the Fourier spectrum of the reduction function f to conclude that the target, the maximal correlation of the target, must be an integral multiple of the source maximal correlation. Suppose the target is rho to the target maximal correlation rho prime is rho to the power k, where k is some constant 1, 2, 3, 4, some natural number. Then we can also conclude that nearly the entire spectral weight of the reduction function is concentrated on degree k terms. In other words, we have proven that the Boolean function f is in fact a homogeneous function of degree k. So that's what we have concluded here. So if we have a Boolean function that has its entire spectral mass concentrated on degree k terms, then we can conclude that it is a Boolean function with low total influence. At this point, we can hit it with a sledgehammer of a Junta theorem. We in particular use the Kindler-Safra Junta theorem that shows that the output of the function f is approximately close to another function, Boolean function h, which is a constant Junta. That is, this h only depends on constant number of inputs. So again, let's go over this result carefully. This is very strong result. It says that the complexity of f is essentially captured by few inputs. The number n is not important. There are only a constant number of samples that influence the output of f. So at this point, we conclude that the reduction function f is close to a Junta function, that depends only on a constant number of inputs. Then we consider the first one of the security constraints, that T bar of H must be close to G. However, using random restrictions, we prove that this must be a positive constant. And this positive constant depends on the maximal correlations rho and rho prime. So we prove that if such a secure non-interactive simulation exists, then it must be constant insecure. So let us quickly summarize the high-level overview of our proof technique. We first have a de-randomization step that says that without loss of generality, we can assume that our reduction functions are deterministic. Then we algebraize the notion of security. Then we reduce the problem to an approximate eigenvector problem. Then we hit it with a appropriate Junta theorem to get Fourier concentration results. And then we finally perform a dimension reduction. I wanted to highlight this high-level template because our proofs all follow this template. So now let us move to some feasibility results. Suppose our objective is to consider self-simulation of binary symmetric noise from binary symmetric source. That is, both the source and the target are correlated noise generated by the binary symmetric channel. We can follow the template that we followed earlier to conclude that the target's maximal correlation has to be integral power of the source's maximal correlation. We again get a very strong Fourier concentration result that says that the reduction function f must have nearly its entire spectral weights on degree k terms. Finally, the dimension reduction shows that f and g, both reduction functions, are close to a Junta function, which depends only on constant number of inputs. So let us look at a few examples to understand how these Junta functions could look like. So we saw earlier that product of the function, the input samples, is a secure construction. We'll say that such reductions are linear because this construction corresponds to a Fourier character. Okay, since it's in this case, the function f and g are both degree 2 homogeneous functions. In particular, there is only one term in the function. There may be more than one, but in this particular example, there is exactly one term. Okay. Fascinatingly, there also exists nonlinear reductions. Let me give an example that achieves the same target distribution SNIS that I explained earlier. However, this reduction uses 4 samples, and the reduction function f is the following function. It checks if the first 2 samples are identical or not. If the first 2 samples are identical, then it outputs the product of the first and the 4th sample. If the first 2 samples are different, then it outputs the product of the first and the 3rd sample. You can, it's clear that this is a Boolean function. This function can be algebraized as follows. So therefore, this gives us the Fourier transform of the function itself. Note that this is a homogeneous function. Each term here has degree 2. However, it's not linear because there is no one Fourier character such that its entire weight is on that particular Fourier character. And we can show that this reduction is in fact secure. So a natural question that arises here is that maybe linear constructions are the best. Maybe nonlinear constructions exist. However, they are always worse than linear constructions. For example, I showed that the linear construction only takes 2 samples to create the target's distribution. Here, the nonlinear construction is taking 4 input samples to create the target. So it's worse rate. However, while studying the rate of such constructions, let's consider these 2 reduction functions. So the first reduction function is exactly the same nonlinear reduction function that I explained earlier. However, the second one is a slight modification of it. Interestingly, these 2 outputs are also secure. What I mean by this is that the output of the first reduction function is a secure sample from the target distribution. This output of the second reduction function is an independent, secure sample from the target distribution. That is, these 2 reductions can output 2 target samples from 4 source samples. These nonlinear distributions also achieve rate half. So let's try to understand what is the current situation. Okay, linear constructions can achieve rate half. I explained earlier using an example that nonlinear reductions can also achieve rate half. Is it possible that nonlinear reductions can surpass rate half? We can in fact prove that the linear constructions cannot surpass rate half. So it's possible that nonlinear reductions can break this bound. However, we prove that if you are considering perfectly secure non-interactive simulation, then it is impossible to break the bound of half, even using non-interactive, even using non-linear reduction functions. However, the case of statistically secure simulation remains open. We in fact have a conjecture pertaining to homogeneous Boolean functions. If this conjecture holds, then our result will extend to statistical secure non-interactive simulation rate as well. So the way I would like to summarize this line of research is that at present, the state of the art in harmonic analysis or characterization of Boolean functions using its spectrum, that is the primary bottleneck, not our cryptographic understanding. So another way to look at our research is that our research motivates fundamentally new research in harmonic analysis and gives additional motivation to study additional motivation for such research. If you are interested, I can discuss on this conjecture offline. So let me move to another connection of our secure non-interactive simulation to distant invariant codes. A distant invariant code is a code if the total number of code words from a particular code word C is invariant of the code word C. We prove an equivalence between reduction functions and distance invariant codes. Given a reduction function, we can consider a code that is the pre-image of +1 and the pre-image of -1, and we can prove that these distance enumerators are actually these codes actually yield distance invariant codes. So we have actually established a connection between secure non-interactive simulation and homogeneous Boolean functions and distance invariant codes. Towards the end of the talk, let me quickly go over to simulating binary symmetric sources from arbitrary noise sources. In this case, we have to upgrade our Hunta theorem to Fredgood's Hunta theorem. And the results in this case slightly change. We do not have a very strong concentration on degree K terms. However, we have concentration on degree less than equal to K terms. And I will show using an example that this less than equal to k, not exactly k, is in fact necessary. Finally, I also want to mention a technical subtlety. We had to go through Efronstein decomposition in our analysis. I do not know whether it is necessary or not. We could not make the proofs work without this. So let me show the power of nonlinear reductions using an example. Let me introduce a source distribution called random oblivious linear function evaluation. In this source, you sample 3 random elements from a finite field of size 2, a, b, and x, and you compute a linear combination ax plus b. Let this result be z. Alice gets the samples a and b. Bob gets the samples x and z. So this correlated this randomness can be represented by this graph, where Alice samples are the left partite set, Bob samples are right partite sets, and the edges indicate whether the samples are consistent or not. So as you can see, this is a cycle of length 8. You can compute the corresponding t bar vector for this source, and you can compute its eigenvalues. Its eigenvalues are 1, half, and 0. So sigma is the smallest square root of the smallest non-zero eigenvalue, and that turns out to be 1 by square root 2. And let us consider a binary symmetric source with probability that it flips the output to epsilon being 1/4. In this case, it's the maximal correlation of this target distribution is 1 minus 2 epsilon, which is half. And our upper bound for rate actually turns out to be half. So if our objective is to simulate if our objective is to simulate samples from binary symmetric source from Rayleigh samples, then an upper bound on the rate is half. So let me first give you the natural question is whether this bound is achievable or not. Let me tell you what we know from the current state of the art. If you use 3 samples of the Rayleigh source and use 1 round of communication, then we can implement an oblivious 1 out of 4 multiplexer. What Alice can then do is that it samples a random bit, creates 3 copies of the bit and 1 copy of the complement of the bit, randomly permutes them and sends them to the multiplexer. Bob chooses to receive one random bit from the multiplexer. So observe that Bob receives the same bit as Alice sent, the bit U, with probability 3 by 4, and Alice does not know whether Bob received the bit or not. So I want to emphasize that this is the current state of the art that uses 3 samples, uses 1 round of communication to achieve what I illustrated in the previous slide. Now, our objective is to use no communication and use only 2 samples. The question is whether such a construction exists or not. And the natural thing that we did was exhaustively search the set of all Boolean junta functions with certain properties. We in fact found 16 such reductions. These 16 such reductions in fact turned out to be essentially identical to a canonical reduction, and let me present that reduction here. So to begin, Alice and Bob have 2 independent samples from the Rayleigh source. Alice gets A1 B1, A2 B2. Bob gets X1 Z1, where Z1 is A1 X1 plus B1, and Bob gets X2 Z2, where Z2 is A2 X2 plus B2. The reduction function for Alice says +1 if A1 B1 plus B1 is equal to B2. And I again highlight that this arithmetic is with respect to the arithmetic over the finite field of size 2. Otherwise, the reduction function is -1, and the reduction function of Bob is same as the reduction function of Alice. So we can actually algebraize this, and this is the reduction function. So this gives us a Fourier representation of the reduction function. As you can see, this reduction function is not homogeneous. It is concentrated on low degree terms. However, again, let me emphasize, it is not homogeneous. We in fact prove that no linear construction can achieve this simulation. So we prove that there exists a nonlinear reduction, and we prove that no linear reduction can achieve this simulation. In fact, we prove a very, very strong result. We show that you can arbitrarily name your samples as you like. Even then, it does not admit a linear reduction. So this result shows that non-linear reductions are inherently more powerful, more expressive, potentially achieving higher rate than linear reductions. And this is something extremely fascinating, which we did not know earlier in cryptography in the context of secure multi-party computation. To conclude my talk, let me just state a few open research directions that are natural extension of the work that we are currently, that I presented in this talk. So we considered some dimension reduction techniques like Hunta theorems. A natural question is whether we can improve such dimension reduction techniques specifically for and design them specifically for cryptographic context where security is being considered. Further, we would like to consider such tools, dimension reduction tools, when the insecurity is not too small and there is practical motivation for such studies as well. And the study of precise feasibility and rate is a natural question, as I motivated earlier. This leads into studying tight monotones for secure computation. Such monotones have been widely considered in information theory, but not in the context of secure computation, or they were not tight enough. Therefore, I'm putting emphasis on the word precise in this context. And just like Shannon's study, can we come up with converse theorems for secure multi-party computation? In the talk today, we considered reduction, two-party reductions that considered samples from one type of source. However, we can consider reductions from a family of sources. These actually give us an extremely powerful technical tool. In fact, think of it in this way. When we say that parties have access to independent private randomness, we can give access to parties, can give access to private randomness as part of this setup. And that study will be folded inside this study automatically. So for example, de-randomization will be a consequence of such a generalized study. In cryptography, we are typically interested in targets that are samples from a discrete source. In fact, it is well motivated that we can consider samples from continuous source, for example, observations of an astronomical phenomena, and studying SNIS in that context is also well motivated. I motivated the results that I presented were particular for two-party case. Multi-party extension of secure non-interactive simulation is also well motivated, and there are several open problems open problems that are of practical interest in that context. Finally, I want to state that there are several feasibility and rate problems that are open for one-way secure computation, and there are several practical applications of one-way secure computation. So if we have tight feasibility and rate results for this problem in particular, then these can lead to more efficient design of cryptography protocols, as well as understanding the limits of efficiency of secure multi-party computation. To conclude, I must thank my collaborators, Hamid and Hai. Without them, these projects would not have we could not have completed these projects. In fact, they have led our group's effort in this research. And I must thank all my funding agencies who over the years have funded my research, which has been broadly based in this broad information theoretic study of secure multi-party computation. Yeah. If there are any questions.
Maji, great talk.
Thank you, Wojtek.
Okay, thank you, Maji. I guess there are no, maybe no further questions.
Okay, then I can leave the meeting, right?
Yes, yes, yeah. So we've recorded, so we can make it available for others who aren't able to make it. So
that's perfect.
Okay.
Thank you. And
Thank
please
you
do send me the link. I think this is put on YouTube, right? Like just send me the link as well, please.
Oh, very much so. Yeah, I can send that to you probably tomorrow.
That's perfect. Thank you.
Thanks.
Thank you.
Thanks, everybody.